is, in fact, a bright background star, and this Hubble view is magnificent. Here are Enceladus, Mimas, Dione, and Tethys orbiting Saturn. Once every 15 years, Saturn's rings and moons are aligned just right so that the moon. Shadows stream across the rings as well as on the planet. This video is a time-lapse that lasted 9.5 hours. Amazing! Going a bit further out, we come to Neptune and its biggest moon. Triton, sadly, we don't have a video, but this image captured by Voyager 2 is gorgeous. 3 days after passing by, Neptune Voyager was able to capture the presence of Neptune and Triton. Before Neptune slipped in front of Voyager's view of Triton, going further out again, we come to the furthest celestial object explored in the solar system. Pluto, as New Horizons whizzed by Pluto in 2015, it turned its camera back towards Pluto to capture the dwarf planet totally eclipsing the Sun. What it saw was dazzling, the sunlight streaming through and illuminating the atmosphere and its haze layers, with the ridges and mountains on Pluto's surface, highlighted by the stark contrast of Pluto's night. Music sidulations and transits may be breathtakingly beautiful. But are they actually useful to us scientifically? Well, did you know that Uranus was discovered to have rings because of an occultation of a background round star, as the planet passed in front of the star? From our perspective, the star dimmed before and after the planet obscured it. With this information, we are able to count how many rings Uranus has on top of that. The transits of exoplanets in front of their stars are actually how we can detect exoplanets. Telescopes like Kepler and TESS measure the brightness of stars in the sky. If a star dims, it could be because one of its planets just passed in front of it. If the star continually dims in a pattern, for instance once every 100 days, then we know that a planet orbits that star and takes 100 days to do so. Using this method, space agencies like NASA have discovered over 3,000 exoplanets, more than all other methods of exoplanet detection. Combined, it can even help scientists calculate the size of the planet by measuring how much the star dimmed or the composition of that planet's atmosphere, by looking at the spectra of the light that passes through from the star to us. It might be some time before we see a solar eclipse again, after the one in April. The next eclipse won't happen in America until 2044, here in the UK. The next one won't occur until 2090. If I live to see it, I will be a very old man, but I'm amazed as I see all of the images of eclipses that take place throughout the solar system. There's a special beauty to each one of them, a fleeting moment, where one celestial body brushes lightly against another, even if it's only through their shadows rather than harbingers of doom. These moments fill me with awe and remind me how connected the universe is, even across thousands, millions, or even billions of kilometers of space. We can notice a planet's passing, and if you're in the right place, at the right time, oh, what wonders you can see. Earth has a pollution problem. There are plastics and landfill items, the types of things you might throw out at home. And then there's dangerous industrial waste, like nuclear byproducts, biohazards, and chemical toxins. These stifle ecosystems and affect the health of vulnerable communities the world over. So far, the best solution we could come up with for disposing of nuclear waste is burying it deep underground. Not ideal, when you consider that the stuff remains dangerously radioactive for tens of thousands of years. So why don't we just strap it to a rocket and blast it into the sun, like launching a missile at a target? Wouldn't that solve all our problems? I'm Alex Molan, and this is Astrom Einers. A big thanks to all of our patrons for making this series possible. If you want to send us your questions, join our Patreon by clicking the link in the description below to begin answering our question. It's actually really hard to crash anything into the sun. Let's take a closer look. Suppose we've gathered together a massive pile of toxic waste destined for the sun. The first thing we'd need to figure out is how to get it into space. Easy, right? We've been launching stuff into space for the better half of a century. To get our trash pack through the atmosphere and out past Earth's orbit, we need to accelerate it to a velocity of 11.2 km/s. This is the speed known as the escape velocity, where the kinetic energy of the payload surpasses Earth's gravitational potential. Energy once free of Earth's orbit, our garbage craft is on course for solar collision, right? Wrong. Once our package escapes Earth's orbit, it's still gravitationally bound to the sun. Put super simply, Earth and everything on it is moving sideways relative to the sun. At 30 km/s, combining this sideways motion with the gravitational pull of the sun is what keeps us locked in an orbit. If the sun worked to somehow lose its gravitational pull, we'd fly right past it at 30 km/s and keep going. If we on Earth were to lose our sideways motion, we'd only be influenced by sun's gravity and fall straight into it, so there's hope for our garbage ball. Yet how could we lose our sideways motion to make this solar free-fall happen? Well, there's two options. The first option is to bring up enough fuel to break in space. Now, technically speaking, you can't really break in the vacuum of space, but the next best thing would be to configure our garbage payload's propulsion system to generate thrust opposite to its direction of sideways motion. This cancels out the sideways motion, slowing the spacecraft down and letting the sun's gravity do its thing.